Um. Following equivalent. One R is zero dimensional. And Noetherian. Two. Any finitely generated R modulus finite length. Number three, R has finite length as an R module. And number four, R is Artinian. And a quick reminder that what it means to be Artinian is it satisfies the descending chain condition. This is actually one of my favorite results, that Artinian is equivalent to Noetherian and zero dimensional. So last time, what did we do last time? We did we made the observation that 3 and 4 were equivalent, given this other information that I had given you earlier, and so last time we did 3 given only 4 and 1 implies 2. So let's pick it up where you left off. Usually only jerks like this. You can see whether this is an exception or not. Well, maybe it's not an if and only if, right? But certainly I think we can agree that 2 implies 3 is clear, right? Because of course R is an R module is finitely generated, right? So the last bit that we need to actually we've already done sort of the heavy lifting. Last bit we want to do is 3 implies 1. That is, if you're Artinian, then you're Noetherian and zero dimensional. Or I'm sorry, not this one. If R has finite length, it's an R module. So notice that if R has finite length, as an R module, it must satisfy the ascending chain condition. Because it's finite fixed length, shows that if you start at any of those points and ascend, you must stabilize. So to show it's zero dimensional, we're going to reduce the problem. In the following sense. Suppose that there's a chain of primes inside M and R. So we have these two primes here, strictly, strict containment in R. Now pass to, here's a reduction. Pass to the quotient R mod P, and we merely need to show that, so if R is a domain of finite length, then it's a field. Yeah. Okay, so to this end, let's suppose that R is a domain of finite length. And choose a minimal, a non-zero. Oh, since R is a finite length, we can choose a minimal ideal non-zero. So you have, well, it's not clear that it's R. Yes. So, since it's a finite length, write down your composition series, write down a minimal ideal. Let's choose a non-zero. We certainly have to be able to do because I is non-zero. And notice that of course, xi is always contained in I, right? But we have equality here because of the minimality of I, right? Because it's non-zero. And so there exists system x alpha equal to x, which is in there. Since R is a domain, alpha must be 1, and hence I equals R. And so R is. Because really what we're saying is a minimal non-zero ideal of R, the whole ring, and so it must be a field. Okay. Any questions on that?
Yes. So when we say it must satisfy ACC, is that because any like chain of ideals is like a subchain of subgroups? And those are
Well,
all
that's right.
finite?
It's because this has a finite fixed length,
Okay,
right? So the composition series. So if you have an ideal, then you can put it in some composition series R. And so since it's finite length, it has, the chain up from that has to terminate, or terminate, stabilize is a better word. So corollary. And this is also, so we're headed toward this business about, overrings of, one-dimensional Noetherian rings. We've been talking about all this kind of stuff, Artinian, which is smaller, lots of zero divisors usually. So here's the connection, or here's a connection. Let R be a domain. R is Noetherian and of dimension less than or equal to 1. These are our coveted conditions here. Noetherian and dimension less than or equal to 1. If and only if for all non-zero ideals in R, R mod I has finite length. So let me sketch the proof here. If R is Noetherian of dimension less than or equal to 1, then what can you say about R mod I? Well, any homomorphic image, the Noetherian ring is Noetherian, right? So this is Noetherian. And of dimension 0. So let me clear this up a little bit. Of course, if R is Noetherian in dimension 0, then the only ideal is RI. So in both cases, it's Noetherian in dimension 0. Actually, in that case, you don't want that to be everything from total equivalence. But anyway, again, the zero dimensional case, just focus on the case where it's dimension 1. If I is a non-zero ideal, then you've gotten rid of since R was a domain, I contains the 0 ideal, so it drops to dimension 0. And the converse of this is clear as well. We're going to use that factoid. So a characterization of Noetherian in dimension less than or equal to 1 is if you mod out by any non-zero ideal, then R mod I has finite length. Okay. Here is another proposition we'll need. You know this one already. It's a homework problem. If R is zero dimensional, then every non-unit and in a zero-dimensional ring, you only have zero divisors and units. Right? This is the exercise on the most recent homework. And here's one last lemma, so maybe I'll put this over here. This is a technical lemma. That I'll record over here, that we'll be using as well. Suppose that R is one-dimensional integral domain. A and C are going to be non-zero elements. Just pick your favorite two non-zero elements of R. If J is the set of so J is sort of this conductor. J is the set of everything in R that blasts some power of A into the ideal C. Then when you take all of J and A, this is equal to R. So J is co-maximal to A. Okay. So this is, so in the proof that we're going to put together, that one-dimensional theory in every overring is still one-dimensional theorem. We're going to use this. So remember this is the characterization. To show that it's one-dimensional Noetherian, just need to show that R mod I is a finite length. We're going to use this proposition from the homework that in a zero-dimensional ring, everything's either a unit or a zero divisor. And this weirdo technical lemma here, this is kind of a weird one, isn't it? That if you have a one-dimensional domain, you pick two non-zero elements. If you look at everything, if you look at the ideal consists of everything that blasts a power of A into the ideal C, then this is equal to R. By the way, is it clear that this is an ideal? All right.
Just take the bigger power of it.
Yeah, right. So let's, I mean, that's not gonna hurt anything. So I'm gonna try to leave this other stuff up as much as possible. So, let's. Then X A N Y A N is in, C. Right. So as you say, we'll take a bigger power. Let's say that N is greater than or equal to M. Notice that X plus Y that's in C and that's in C. So this is in C. So it's closed under addition. It clearly contains zero. And certainly it must be a vacuum cleaner, right? Because if X blasts power of A into C, then R times X will blast that same power in higher of A into C, right? So, all right, so for sure that's an ideal. But again, it's interesting that it's co-maximal to the ideal generated by A. So let's see why this is true. Notice that of course C is in J, right? That works out nicely, alright? So, in particular, J is not the zero ideal. Right, so we've got that going for us. Hence, R mod J is zero dimensional. Right, because J is, R is one dimensional, J is not the zero ideal. So when I crush out, when I do this quotient here, then it's zero dimensional. Because in this, is that clear to everybody that in this, you know, I've done this a couple of times. Here's what happens in R is at the R level, you have maximal ideal zero. Right, that's what something looks like, because it's one dimensional, and zero is a prime because it's a domain. When you pass to R mod J, well, there should be a one-to-one correspondence between primes here, primes here, and primes of this that contain J. Well, that eliminates the zero immediately. So the only ones are the form M mod J, so it's zero dimensional, so all primes are maxes. So this sucker is zero dimensional. So every non-zero divisor in R mod J has an inverse. That is, of course, using proposition 528. I claim that the coset A plus J, that is the image of A down in that quotient ring, is not a zero divisor. Notice that if so suppose I have a product of two things in R mod J, it gives me zero, then the coset representative of the thing that kills it has to be such that AB is in J. So let's write this down. Note that because AB's already in J, I mean, I'm already saying something. Therefore, B is in J by definition, because B tosses a power of A to the N into C. And so this means that, so A plus J is a unit and this means that therefore there exists B in R such that A, B, I'm a little premature here. There exists B in R and little j in J such that A, B, plus J equals one. Therefore, the ideal generated by J and A is all of R. And there's our little lemma. Okay, any questions on this? Okay. All right, so here's our okay, just for the sake of continuity in the notes, I'm gonna state this again. Theorem. To N. If R is one-dimensional and Noetherian, and P is, well, the quotient, okay. And P is proper, proper overring, and of course, proper, I mean, with respect to the quotient field, it can be R itself. Just not the whole quotient field. P is also one-dimensional and Noetherian. Well, let me again point out that if you take off the strictness here, if you allow this to be equal, what you lose is the one dimensionality, right? Okay, so let's go through this, see if we can slog our way through this. Here's our strategy. Our strategy is, we will show that T mod AT is a finitely generated R module. So why is the strategy going to work? Well, note that so what we really want to do is show what the T mod I is finite length for any ideal I and T, right? But note that T mod I is T mod AT mod I mod AT, right? So what's the point of this? The point is, this is what we really want to show has finite length. But if this has finite length, then its homomorphic image T mod I does. So we can reduce to looking at this here. And you might say, but Jim, A was in R. That's okay, because T is an overring of R. And so if you take any ideal, any non-zero ideal of T, it has to contain an element of R. right? Just by multiplying by whatever the appropriate denominator is, and you can blast it down into R. So we can reduce this a little bit by looking at T mod AT for some element A and T. If we can show that that's finitely generated, then we're good to go. Because the rest of it will follow. So that's where we're going on that. So in our attempt to show that this is a finitely generated module, we're going to write I want to define this family. It's going to be a descending family of ideals. This is a descending chain of ideals of R. All containing AR. Right, notice, of course, each one of these, notice these are, of course, ideals of R, because this is an intersection and this is another generator. So it's basically, what you're doing is you're looking at what is the nth power of A generate as an ideal up in T, intersect that down to R and throw in A as another generator in case you don't get it, right? And this forms a decreasing chain of primes. Of course, as the n gets larger, this gets smaller and smaller. Right, and of course, all these ideals contain AR, and we're going to quotient out by that at the last minute. So this decreasing chain of ideals will stabilize. Why is that?
When we quotient out, we get a module finite.
That's right, that's right, that's right. There's no reason to think that this decreasing chain of ideals, an arbitrary decreasing chain of ideals in R is going to stabilize, right? In fact, it shouldn't, because R is one dimensional, right? But there's something special about this, and that is they all contain AR, right? And so if you mod out by AR, this becomes a decreasing chain of decreasing chain of ideals in R mod AR, which is Artinian, because it's zero dimensional now. And so now, because basically what I've done is, instead of like going all the way down into zero, all the way into the pits, this is sort of a platform. You can never go below AR. And so that means that this must stay here, right? And we'll say that it stabilizes at some n. It's because all contain AR and R mod AR is Artinian. We say chain stabilizes at I. Okay. So I'm gonna make one of my patented claims here. Here's my claim. For this value then, we have that T is contained in 1 over A n R Himself. Oh. Plus my mind. There we go, plus. So for this value of n, where this decreasing chain of ideals stabilizes, I can, I claim that the T, this set is actually contained in 1/a(n)(r) plus AT, right? So anything in there can be written as something in the ideal generated by A plus adjusted by 1/a(n), something in R. So let me justify this claim. Of course, we're talking, T is an overing R, so I can write it as a fraction of, two elements in R. And now take A and C as in lemma 529. Right, the C is, already given to us, obviously C has to be non-zero, take some other non-zero element A. Well, no, actually, we've got A as well, but take AC. Let me say it this way, and apply, let's go away. Limit, 529. We have that J A is equal to R, right? Where J is this, craziness that we defined over here. Okay, so what does this mean? So we can write we can write, one is J plus some, call it here, ZA. J and J, and Z some element of R. So, now we're going to manipulate this a little bit. So T, let's write this down, given what we've got, T is plus, TZA. I'm gonna write this way. And of course, this is just from multiplying this by T and writing down, oh, I meant to, but it's supposed to be a J. Why did I check that? Right. So this is just multiplying this by T. There's your J. We wrote, T is what it is here. We left it in the convenient form here. T. So recall, of course, J is in this crazy ideal right here. So there's some power of A, we'll say the kth power, such JAK is in C. So we can write BJ over C is equal to BC over JAKAK. Like that. And the point is, what is the point of this? Well, JAK, this piece right here, is in the ideal generated by C. So this thing right here is a multiple of C, which cancels a C down here. So this is actually in 1 over A to the K R. Right, because this is some R times 1 over A to the K. Right?
You stabilize at n, that's a subset of one over eight, yeah.
Right, well, so this is for some K, there's still some stuff we've got to patch out here. And I think I've used this enough here so I can. So I've got this BJ over C is my piece that's in 1 over AKR. And what's left over here? So if you look at T, so we've got T is actually in 1 over AKR. Caveat, for some K. So we've got almost what we want here, right? But not quite, because I need this to be an N here. So in particular, we're good to go. So K is less than or equal in, we're good to go. So let's discard the case. What happens if K is bigger than N? Let's assume that K is bigger than N, but is as small as possible. So suppose that this doesn't work out for us. My K has to be bigger than N. Let's find such a counterexample that's minimal. So what do we have here?
Can you use the fact that changed twice, right?
What's that?
You can use the fact that changed twice at n, right?
That's exactly what we're going to do, as a matter of fact. So what we have here is we have T. We have T is equal to U over A to the K plus AT1. Right. And hence, if I solve this for U, if I solve this for U, I get U is equal to A to the K times quantity T minus AT1. That's what this U gives us. And here, you're exactly right, that this is where we use the stabilization. So U is in, A to the KT, and R. And so U is in, IK. Since K is bigger than N, we have IK is equal to IK plus one. And there's the stability, the stability thing we're, looking for. And so we can write U is equal to AK plus one, T2 times AU1. Right. And then we substitute. The following equation. T is equal to is equal to U over AK minus one, times A or plus A. And this gives a contradiction. And what have we contradicted? We've contradicted the minimality of the. So, this gives us the veracity of our claim. That is, T is contained in one over A N R plus A. So, notice that T mod AT is now contained in a cyclic R module, right? Because T is contained in this cyclic R module, adjusted by this. So T mod AT is contained in that cyclic R module. And so, again, recall that R is Noetherian and T mod AT is inside the cyclic R module. So, is contained in a cyclic R module. Finally, generated is certainly true. So T mod AT is a finitely generated. And that wraps it. Any questions? All right, well, put this in your pipe and smoke it, and see if you can, if there's any details that aren't clear, we can talk about them. Don't forget in the math club today, Ben Gobbler is talking and his talks are probably not to be missed. So I would encourage you all to be there. Other than that, y'all have a great weekend and we'll see you on Monday.